Thank you.
Okay, well, welcome back, viewers online. Without further ado, because time's running out, hand over to my colleague Michael Reid, who is going to be talking to us on engineering a circular economy in nutrients.
So, welcome everyone to the second half. Engineering a circular economy in nutrients is not something that's much looked at, not much talked about. But in fact, it's a huge issue that needs to be dealt with. We're talking a lot about energy and emissions, and this is a story about emissions as well. But what it's also a story about is how we use the materials of the world effectively. And this, I'll give you a particular example of this, but it counts for many other industries. There's a clue to the answer in the quote there, but I'll come back to that at the end. Whoop, there we go. Let's start with emissions. This is the UK. You might notice there's a big green blob there. The big green blob doesn't mean it's the sustainable bit, it means it's agriculture. So why is agriculture so emitting? Well, you might have noticed a couple of weeks ago when gas prices went through the roof, one of the first things that happened was fertilizer production stopped. There had to be government intervention to start it up again. And still farmers are no longer spending £250 a tonne for their fertilizer, it's up at £700 a tonne. This gives you an idea of the massive dependence that agriculture has on fossil gas. This is emissions writ large, and a large proportion of the world's emissions are coming from agriculture and a result of agriculture. That's just the beginning. So, talking about the world, here we are. But there's a success story to talk about agriculture. Agriculture has been something which has gone through a massive revolution over the last few decades. Production has quadrupled, which is just as well since the population has almost done the same. But interestingly, the number of starving people in the world has been a steadily diminishing number. This is a good thing, except that it's been at the because we're using chemical fertilizers. So, what do we do? Well, do we keep doing the chemical fertilizers and all the emissions? Well, we can't. Not just because of the emissions, but because there are other bits of fertilizers that are and have a limited supply. They are not sustainable. So there has to be a way to make this circular. How does it work at the moment? Well, at the moment you dig up minerals, phosphates in Mauritania or China. Ever heard of Mauritania? No, it's not in Eastern Europe, it's in Africa. It's a conflict zone because it has a massively important resource in it, phosphates. You notice that massively important resources seem to follow conflict, or the other way around. I won't go into that. So if we can have a circular system, which doesn't involve digging it up, processing it, putting it on the ground, eating the stuff, flushing it down and disposing of it, which is a straight line process, then we can do something about this problem. So, what's the answer? An answer is to see where these go. Follow the minerals, follow the nutrients. And this is one of the places where they end up. Not the only place by any means, but in water treatment works. Resources held in wastewater are of enormous value and in huge quantities, and other waste streams as well. And if we can find new routes for returning nutrients to the economy, then we have some of the answer to the first question. So organomineral fertilizers are part of the solution. And they're conventional in so much that they're used in the same way as current fertilizers. And it's a hugely expanding sector. and has standardized nitrogen, phosphorus, potassium formulations. But the organic contents are massively larger. In fact, they can be up over 50%. So what does that do? Well, these fertilizers are less polluting. So the nitrogen, phosphorus, potassium doesn't do what current fertilizer, nitrogen, phosphorus, and potassium does in large quantities and run off into the watercourses or down into the aquifers. It tends to stay on the field and get released slowly. Volatilization is a massive issue with fertilizers. Any agronomist will say if you put urea on a field, you get the crop growing really fast, but it only uses half of that. The rest turns into a mixture of ammonia and laughing gas, which is no laughing matter because it's a hugely nasty greenhouse gas. It's the third most important greenhouse gas after carbon dioxide and methane. So they allow lower nutrient application rates to the field, better soil health, better nutrient levels in the food. Your typical apple that you buy in a supermarket, there are records of nutrient quantities and nutrient levels in having from back from 1960, and it shows that they've halved on average. So the amount of nutrition you get from your apples is half now what it was in 1960 on average. Our food is less nutritious. It's actually less tasty. If you're as old as me, you might remember it tasting a bit better. And it's not just the aging process. So it also has the capacity of restoring carbon into the soil. Soils have been losing carbon on a massive basis. So it gets a chance of reversing. So what is happening in this country with fertilizers? Nitrogen, you see lots of nitrogen, phosphorus, potassium getting thrown on the soil. I say thrown on the soil, that's literally what's happening. This is 2018's figures. Now, in human waste, and food waste and animal-based food materials, there is available a large amount of nitrogen, also phosphorus and potassium. And anyone who can do a bit of quick mental math will see that what we need is less than what we actually produce as a country in the way of waste. How can that be? Well, we may look at it as an import-export situation. If you are importing food, you're importing nutrients. If you're importing cattle fodder, you're importing nutrients. And all of those nutrients being leached out of the deforested land in Uruguay end up on our plate as a steak and as manure on the farms and food waste. So the nutrient has a path, has a trajectory. They travel around the planet, and they travel around the planet in the form of fertilizers and the form of food. So we could be net exporters of fertilizer rather than net importers of fertilizer, if only we could get these resources into a usable form. Now, what do they come in? They come in several forms. Partially digested organic derived carbon, sorry about that, otherwise known as anaerobic digestate. A huge proportion of the organic material waste producing industries use anaerobic digestion to produce green gas. It's a great thing. Zero carbon gas. It's useful. It goes into the grid, gets burnt to make electricity without any net emissions. This is good. However, it has a huge amount of what's left over called digestate, which has to be dealt with. And that's where all the nutrients are, fortunately. But they're very, very unstable. If we could stabilize it, there would be a market. We could sell 12 million tons of it annually. In this country only, But a big challenge is that the competition between the water sector, the agricultural sector, the food industry sector, and places to put the digestate is put on land at the moment. So you think, well, that's the answer, that's the question answered. No, it's not. Now, if you thought urea was bad, if you put anaerobic digestate on a field, the wash-off is enormous. Anyone driven past a field which has just been dosed with, yeah, exactly. It stinks. And it stinks because of the ammonia, it stinks because of the methane, it stinks because of the laughing gas. Yeah, this is all sorts of things that are being lost. This is lost nutrients. All of it is lost nutrients. If we can stabilize it, then we have a huge opportunity. Washing off, washing in, volatilization, it's a big topic at the moment, but sewage that isn't actually going where it needs to go. 400,000 times in the UK alone last year. This is not good use of nutrients. So, but it's a potential opportunity. If, say, we manage to only get a small proportion of that being sold by 2030, that's a million tons. 320 million pounds. That's money that's going into the economy that wasn't there before. Carbon credits, and what happens with people who cannot stop emitting? Well, they buy carbon credits from people who are sequestering carbon into the soil or somewhere else. At the moment, they're about £30 a tonne. You could by 2035, people are talking about £100 a tonne. So that companies can go to the net zero they will be legally obliged to do. This is a massive extra revenue stream for people who are processing waste. So we're not looking at a cost here, we're looking at an opportunity. And you can avoid the emission of the carbon which is emitted in producing the fertilizers in the first place. And that alone is 1.5 million tonnes annually. Big figures. So here's an example, and it's only one of many, of a plant that actually does it. This is the engineering. Okay, sorry, I was going to talk about engineering, and I've got there. Sorry it's taken so long, but you needed to understand what the opportunity and the problem is. So if you take anaerobic digestate cake, you can use a wonderful material to stabilize it and to stop it volatilizing. And that material is called carbon dioxide. So if you mix carbon dioxide in certain ways with this cake, you can stabilize the ammonia, you can stop it being emitted. Where do you get the carbon dioxide? Well, fortunately, if you're putting gas to grid from your anaerobic digestion, you're splitting methane and carbon dioxide, which is also produced in anaerobic digestion. It's a material that is there and currently being thrown into the sky. So it can be used to stabilize that. And balancing nutrients can be added then from all sorts of other areas, sustainable areas. The controversial field of biomass power stations, they produce large amounts of clean wood ash, which are massive sources of nutrients, very valuable ones. And you can pelletize it all up and turn it into an analog of chemical fertilizer. That sounds easy, it isn't. And the sectors of wastewater, food waste, agricultural supplies, all of these resources can be used that are currently disposed of and cost money to dispose of to make something of value. To give you an example, every ton of anaerobic digestate that gets put from a waterworks onto a field costs around about £35 to put there. The farmers will not pay for that. In fact, they are encouraged very strongly to take it because the water industry needs to get rid of it. So it's a negative cost, and it's the opportunities to turn it into a positive one. So in short, you get biosolids, you add ammonia and phosphorus and CO2, and you get this magical chemistry going on. It's not magical chemistry, it's just chemistry, sorry. Then you add a few recycled nutrients, and you end up with something that does exactly the same job as a chemical fertilizer. So, the engineering takes time. Anybody who thinks that engineering is quick is not an engineer, probably. Getting all the solutions. Yeah, let's get all the solutions. It was mentioned earlier in an earlier talk that technology isn't keeping up with the requirements of the problem. And there are reasons for that, and not all of them are engineering reasons. But for you to engineer it, you have to make prototypes. You have to make small scale examples of it. Make mistakes, get it wrong, put them right. Scale it up, find out what problems come up when you scale it up. Then you have to demonstrate it. Why do you have to demonstrate it? Because people need to give you money in order to make it happen. And if you can't prove that it'll happen, nobody will give you any money. So it takes years and years and years to do this. And the biggest constraint of that is not the availability of engineers or the skill of engineers. It's the availability of money. It's people believing it can be done and putting their money after it. You don't believe that there are lots of technologies out there. Go to the Solar Impulse Pavilion down the road there, and you will see 1,000 technologies, different technologies that are part of the solution to the sustainability problem. 1,000 of them, and they aren't the only ones, they're just the top 1,000. I'm very honoured to have developed 2 of them. So this is what engineers need to do. They need to solve the problems, and they are solving the problems. And there are hundreds of thousands of engineers solving the problems. And I tell you what, one of the things that I can say is it's very, very satisfying to be part of the engineering transition of these technologies. That's one of the most satisfying things I've done in my life. So, but the technology has to go into what's there already. You can't say, oh no, you have to tear everything up and put something new in, because that costs money. You have to follow the money. If something isn't going to make a profit, making it happen is difficult. Why do you think there are so few carbon capture and storage plants? It's because it's a financial and energetic parasite on the power plant. Yeah? If you want to make a sustainable technology happen, it needs to make money. And that's one of the criteria that these thousands have. And this particular technology that you're looking at on the screen now. So it has to fit in, it has to make sense. It has to use technology that is available as much as possible. You have to be able to get all the feed streams in place. And you have to make it all go together and work. And so sustainability does not have a cost. It has a cost benefit. This technology and all of those 1,000 will make it cheaper to do things. It's not more expensive to be sustainable, it's cheaper. Now, ask yourself, how expensive is the fuel for this? Well, actually, not at all. It's currently costing somebody something to take away. How expensive is the fuel for solar panels? No, not going to cost there. How expensive is the fuel for wind turbines? Any government that tells you it has to build coal plants has politicians that are being funded by the coal industry. Sorry, politics, I'll stop. But you get the picture. So it has to be cost positive, it has to be making money, and one of the biggest revenue streams is getting rid of the carbon, people who can't stop it. Here's an example, potato waste. You pick potatoes, you make them into crisps, you anaerobically digest their peel, you make fertilizer out of the peel, and then you put fertilizer on the potato field. It's circular economy. Walkers, they're doing that right now. And this fertilizer, when the trial started 7 years ago, was proved to be as good as chemical fertilizer, and it has got steadily better from then onwards. So it is a better fertilizer. Farmers love it. And it improves soil fertilizer fertility through the use and tucking away of carbon dioxide. It sequesters carbon dioxide. It helps the retention of nutrients and moisture. The bugs love it. The natural bugs in the soil love it. Somebody talked about fungi earlier. And fungi under the soil are incredibly valuable. pH mitigation helps to control pH. It makes plants more resistant to drought. It increases the soil organic matter, which has been reducing for decades. Less runoff, less run-in, less volatilization, slow release of nutrients, and micronutrients, all those things that make the food taste nice. In short, CO2 allows the stabilization of ammonia. It allows nitrogen to be released slowly. You get chalk produced as part of the process. Ask a geologist how long that lasts. There's carbon capture for you. And you get greater nutrient density, and you have superior qualities to existing products. You are locking away carbon by avoiding it and sequestering it. And if you think it's a bit of a pipe dream, only 50 of the units that you saw earlier on would produce 1.75 million tons of carbon dioxide reduction. That's the equivalent of taking 375,000 oil-burning cars off the road every year. So, not only are we doing what Mahatma Gandhi meant, which was putting the dung on the fields and the compost, it's making sure that dung and compost has all of its nutrients going to the plants, not just half of it. So thank you very much. Any questions?
Thank you very much, Michael, for that fascinating presentation, and thanks for keeping it within time. We have just a very short time for questions, but can I ask if anyone in the room has a question for Michael?
Just a brief question. Are you sure it's just money? There's billions swilling around in Edinburgh looking for a home. The Americans got to the moon in 10 years by taking a different approach. Your 1,000 solar things down there depress me. We need vast scale.
Exactly.
And I think it's not just in need of money.
Well, I'll tell you a story about that particular technology, which answers your question.
Yeah.
These guys who did this spent years scraping around for bits of cash here and bits of cash there. And it wasn't until they built the demonstrator that the money came. That 7-year process could have taken 3 if the money had started at the beginning. As soon as they demonstrated it, people were snapping their hands off to invest. They're having to turn investors down, seriously, and a lot of them. So it's as soon as you can demonstrate it, as soon as you can show the cash positivity in real life, show me the thing, then it happens. And where the money is needed is at the beginning of that journey for those 1,000 technologies. If they had that investment now, we could halve the time it takes for them to get to market and stop at least half of them who are going to die before they do, dying before they do. It's a massive, massive, massive issue.
So you're actually talking about seed capital, aren't you? You're wanting
Absolutely.
more seed capital for things.
Yeah. There are very, very clever people out there doing very, very clever things, and they're being massively underfunded at the early stage. Seed funding.
You had a
Thank you, Michael. It's great. In the past, derivatives of sewage sludge put to land have problems with heavy metals, which farmers have been concerned about because of toxicity in food production. How does this process deal with the heavy metals in sewage sludge?
Okay, well, in the early days, you just pick the sludge that doesn't have it in. So you start by selection. But actually, there's a lot of work going around the planet, actually, mostly in universities, of finding ways of not getting rid of the heavy metals, but making them insoluble. So they still go on the field, but they never go anywhere. The plants never eat them. And this is, if you buy a packet of fish blood and bone in the garden centre, it says this is a 393 fertilizer. So 3 of nitrogen, 9 of phosphorus, and 3 of potassium. Sorry, the other way around. And then you see the available nutrients at the bottom. It's tiny, because a lot of that will never ever get to the plants. And the stuff with heavy metals, you make sure that they are locked up so they don't get to the plants. And there are lots of very clever ways of doing that. So that's the next stage. Thank you. So,
Yeah,
Thank you. You mentioned in your slide retrofitting. So it's a vision that you would have different scales of this in basically any process that has waste.
absolutely. Any process that has nutrient waste. Yeah, so we're not proposing to go into nuclear waste recycling with this particular technology, but if you have to fit it in. So everything from the one digester farm that produces 2,500 tons of dry digester every year. That farm, if you do the math, you'll find actually that they only need a third of it. Goes back to my initial thing, and the other 2/3 can be sold. So it becomes another revenue stream for the farm, but also a cost saving from the fertilizers that they don't use. So it's a massive upgrading of the material.
Right, thanks very much for that, Michael. And can we thank Michael for that excellent presentation? I would add that there are some very useful comments online, much too long for me to read out, unfortunately, but I'm sure Michael will pick up on them in due course.
Very happy to do so.
We have a couple of minutes left, so remains to me to sum up, which I think we've had 3 very different but very complementary presentations this afternoon, all looking at the kind of engineering that we need to do, because we in ESG at least are engineers. We're sometimes accused by our colleagues of not doing much engineering. I think we do a great deal of engineering, we just do it differently. In order to help mitigate climate change. So I want to thank all 3 of the speakers, or 4 of the speakers, in fact, in 3 sessions. Yeah. Excellent job. And I want to thank those of you who come here today for being with us, and especially for the large number of people who've joined online. I hope you found that fascinating presentation, and a little different from what you normally hear from engineering institutions. And finally, I want to thank our colleague, ESG colleague Daphne, who has organised, pretty much organised this conference for us and obtained this venue for us, for which we're very grateful. And I think it's been a very enjoyable time. So without further ado, hang on time, I declare the conference closed.